Okay friends, we are looking at Hcverma solutions. We are doing rotational mechanics. Hcverma exercise we are planning to solve certain complex sums. So we are doing Hcverma rotational mechanics and chapter 10 I think it is. It is on page number 200 and we are going to solve example number 76. You can refer the textbook for the statement of the problem. There is a hollow sphere which is rolling down this incline. There is a hollow sphere which is rolling down the incline. This inclination is given to be theta. We are supposed to find the minimum value of coefficient of friction so that the sphere rolls without slipping. The sphere is released from rest at this point. At this point, it is rolling down. We are supposed to find the minimum value of coefficient of friction for the sphere to roll. Now you know the rolling without slipping, the required condition is that V must be equal to R omega. Now please see that as the sphere starts rolling down, the gravitational force is doing work on it. So there is going to be acceleration due to gravity. Let me resolve the weight. Weight is mg. Here we have a normal reaction exerted from the surface. If this angle is theta, from geometry you can very easily get this angle is also theta. This component will be mg cos theta and a component along the plane will be mg sin theta. So this particular component of force mg sin theta will continuously increase the velocity v, and therefore as v increases, omega also must increase to maintain the relationship v equal to r omega at any instant. For omega to increase, there has to be a rotational torque, and as the sphere is rolling in this direction, the torque also must move in this direction, and this torque is provided by the frictional force, and obviously the direction of frictional force must be this, so that it will produce a clockwise torque at the center, and this clockwise torque at the center, the clockwise torque at the center will produce the required angular velocity. So the force of friction must be in this direction. Now let us see the situation. We are going to find velocity as well as omega, and then we are going to use the relationship v is equal to r omega. Let us use Newton's equations of motion, and before that we will use the D'Alembert's principle. What is the net force in the downward direction? Mg sin theta minus F. So according to D'Alembert's principle, mg sin theta minus F gives you me. This is the first relationship. Okay. So that gives you the value of acceleration A as mg sin theta minus F upon. Correct. Now let us consider the rotational aspect of it. The torque produced at the center is F into R, where R is the radius. Let us take R as the radius of the sphere. So F into R is the rotational torque. This torque is equal to I into alpha. Let us take I as mk square in general, where k is the radius of gyration. We can put the value afterwards. So you get F into R is equal to mk square into alpha, and that gives you alpha as F into R upon mk square. So this is alpha and this is A. Now what we will do is we will use Newton's equations of motion. V equal to u plus at and omega equal to omega naught plus alpha t. So let us use these Newton's equations of motion. So we have V equal to u plus at and u is 0 anyway. So you get V is equal to at. On similar lines, omega is equal to omega naught, which is the initial velocity. As it is released from rest, omega naught is 0. So omega will be alpha t. So what is V upon omega? V upon omega will be A upon alpha. Now for condition of pure rolling, what do we have? We should always have V is equal to R omega, or V upon omega must be equal to R. So if I put it over here, we will get R equal to A upon alpha, or in other words, you will get A is equal to R alpha. Take a good look at this situation. A is equal to R alpha is applicable if and only if the rolling is pure without slipping. This is applicable in any situation. Please remember this. A is equal to R alpha can be applied only in case of pure rolling. Now I am going to put the values of A and alpha from what we have obtained here. Take a good look at the values of A and alpha again. Look at this. This is A. mg sin theta minus f upon m, that is A. Just a second. So A is mg sin theta minus f upon m is equal to R, and what is alpha? Let us take a look at alpha again. Alpha is fr upon mk square. See here, alpha is fr upon mk square. Again I am going to substitute it. Now using this relationship, I am going to find the force of friction. So let us rearrange the terms and get F on one side, so that we will be able to obtain the value of frictional force required for pure rolling. This is the minimum force of friction which is necessary for rolling, and in this case the rolling will be pure without slipping. So let me cancel here m and m. So I have mg sin theta minus f is equal to f into r square upon k square. F will come on this side. So this is the general expression. Please note, this particular expression can be used for any body: cylinder, sphere, hollow sphere, solid sphere, disc, ring, anything. You can use this equation. Now for a hollow sphere, you know the moment of inertia is 2 by 3 mr square. So when we are talking about a hollow sphere, as it is given in the problem, the moment of inertia mk square is given by 2 by 3 mr square, and therefore r square upon k square will be 3 by 2. Let us put it value over here, and what we will get here is mg into sin theta is f into 1 plus 3 by 2, that is F into 5 by 2. So of course 5 by 2 goes on the other side, and you get the force of friction as 2 by 5 into mg sin theta. So this is the value of force of friction that is required for pure rolling, 2 by 5 into mg sin theta. Now we are asked to find the coefficient of friction and not the force of friction. So we need to take one more step in order to find the value of coefficient of friction. अपने लिए sufficient? Sure? So we need to find, we'll take one more step. Let us go back to previous page and see the coefficient of friction, how it is related. You can see here that the normal reaction N is balanced by mg cos theta. So N is going to be equal to mg cos theta, and the force of friction is mu into N, right? So we will get a relationship. N is equal to mg cos theta and F is mu into N. So we'll use that. And therefore what we have is 2 by 5 into mg sin theta is mu, and what is N? N is mg cos theta. mg will cancel, cos will go on there, will become tan, and you get the value of coefficient of friction as 2 by 5 into tan theta. So this is the value of coefficient of friction which is required so that the sphere can roll immediately without slipping, that is, it will have a purely rolling motion. The answer is 2 by 5 tan theta. Now the next part of the problem, example number 76, the next part of the problem is really complicated. It's really complicated. It is asking us what will be the situation if the coefficient of friction is not 2 by 5 mg tan theta. In fact, if the coefficient of friction is half of that value. So now the coefficient of friction is half the value which is necessary for pure rolling. Now if coefficient of friction is not sufficient to cause pure rolling, it means there will be rolling as well as slipping. So now we are faced with a situation where there is rolling also and there is slipping also. So if F is less than the minimum required value, we have to consider both rolling and slipping. And they are asking us a very intricate question. They are asking us to find the kinetic energy of the ball or the sphere as it moves through a distance L down the incline. So now we are facing a slightly complicated situation, but let us face the situation and see what to do. So they have given us the coefficient of friction is not 2 by 5, it is half of that, so it is given mu as 1 by 5 into g tan theta. Now V equal to R omega will not hold, because for V equal to R omega to hold, mu turns out to be 2 by 5 g tan theta, correct? So now let us use again the same equation. Let us find the acceleration. The acceleration will be given by again mg sin theta minus force of friction, which is mu mg cos theta. Let us put mu as 1 by 5 g tan theta and see what we will get. We will get, this is multiplied by mg sin theta minus mu is 1 by 5, not g, sorry, g into m into cos theta into 1 by 5 into tan theta equal to m. And that gives you, if you cancel mass, you will get g sin theta minus 1 by 5 g, and cos into tan is sin. You have cancelled m, so that gives you a as 4 by 5 into g sin theta. Please remember this value, that under the given circumstances, when the coefficient of friction is 1 by 5 tan theta, the value of acceleration turns out to be 4 by 5 g sin theta. Now let us try to find the value of omega. Again we are going to use F into R is equal to I into alpha, and that gives me the value of alpha. F is mu mg into cos theta. I will take I as mk square. Mu is 1 by 5 tan theta into mg into cos theta is equal to mk square into alpha. Let us cancel mass. Tan into cos gives you sin, so this is gr sin theta upon phi k square. You see here, g r tan into cos is sin upon phi, and this k square comes down, so g into r into sin theta upon phi k square. This is the value of alpha. Okay, now we are supposed to find, let me write down these values so that we will use them. And what was A? I think it was 4 by 5 g sin theta, but let me confirm. Yeah, it was 4 by 5 g sin theta. Now we are again coming back to using Newton's equations of motion. So let us find out the energy. Now there will be two types of energies. One will be translational energy and other will be rotational kinetic energy. So let us first try to find out the translational kinetic energy. We will use Newton's third equation of motion, v square equal to u square plus 2as. The distance given is L, so we will use v square equal to u square plus 2al. U is 0 because it is the initial velocity, so v square will be 2. What is A? A is 4 by 5 g sin theta into L. So what is the kinetic energy translation? Half mv square, and that will be half into m into 2 into 4 by 5 into g sin theta into L. 2 will cancel, and your translational kinetic energy will be 4 by 5 mgl into sin theta. This is your translational kinetic energy. Now we have to find the rotational kinetic energy. In order to find rotational kinetic energy, we must find the value of omega. by the time this much of distance is traveled. So once you find omega, you can use half I omega square, and then you can get the answer for the rotational kinetic energy, which is half I omega square. So now let us find out how much time is required to cover a distance L in translational motion. Let me write this result on the right hand side. We have got E translational as 4 by 5 mgl into sine theta. Okay, now you know v square equal to u square plus 2as, so that we already know. So we know v is root of 2al, and this v is also same as at. So how much time is required? The time required for covering a distance L is given by 2al upon a, and that will be root of 2l upon a. Correct. At the end of this time interval, let us find out what is the omega. Omega will be alpha t. So omega will be alpha, which is gr sine theta upon 5k square into t. T is what? T is root 2l upon a. What is a? A is 4 by 5 g sine theta. That will substitute afterwards. So this is omega. At the end of time interval t, the value of omega is this: gr sine theta upon 5k square into under root of 2l upon a. I hope you have got this clearly. Please see here. You can also get this relationship by using L equal to half at square. Same relationship you will get. That is second equation of motion. S equal to ut plus half at square. You will get t as root of 2l upon a. Omega is alpha t, alpha into t. Now let us find out the rotational kinetic energy. It is given by half I omega square. Which is half I is mk square, and please see omega square carefully, otherwise it will push us into trouble. G square r square sine square theta upon 25 k raised to 4 into root will go, so 2l, and what is a? Let me put a here now. 4 by 5 g sine theta. Now, unless we do this carefully, we are going to land into trouble, because it is a big thing. So let us first take the numerical values. What do we have in numerical values? Let us see. Let's get rid of 2 and 2. I've got 25 into 4 by 5, that is, I think, 1 by 20. Then we have k square upon r square. G will cancel, 1 g will cancel, so what remains is g. 1 sine theta will cancel, so sine theta, and L will remain as it is. Now you know k square upon r square is 3 by 2 for a hollow sphere. You have already seen that. Of course this m is there, and that gives me the rotational kinetic energy as 3 by 40 times mgl sine theta. So the total energy of the system is sum of translational plus rotational. So let us do that. Total energy will be sum of translational plus rotational. So it was 4 by 5 mgl sine theta plus 3 by 40. Let's take mgl sine theta common. Please do this calculation. LCM is 40. So 5 8s are 48 for the 32 plus the 35. You can divide by 5. And if you divide by 5 and take the ratio, then we will get the final answer as 7 by 8 mgl sine theta. So this is the total energy as the body rolls down through a distance L under a condition when there is slipping as well as rolling. So the answer is 7 by 8 mgl sine theta. Now there are different aspects to this problem. Suppose they ask you in the same problem, let me extend it. How much work is done by the friction? Suppose they ask you this. How much work is done by the frictional force during this situation? So we'll try to understand that. Please see that when there is rolling, friction does no work. The friction will do work only when it is slipping, that is when there is a skidding happening, then only the friction is going to perform work. So now we are going to find out how much distance out of L is spent in skidding and how much distance is spent in rolling. So we are going to try to make an attempt to find out that value. Let us again get the values of omega and A on the screen. A is 4 by 5 g sine theta. And what was alpha? I missed alpha. Anyway, let us calculate alpha again. A is 4 by 5 g sine theta. I'll just do it quickly here. F into R. F is mu, which is into mg into cos theta into R, and that gives you alpha as gr sine theta upon 5k square. Now let us consider, we are going to find out now what part is covered. For that you will use S equal to ut plus half at square. So you have S is equal to half at square. You can write S as L because they have given L, and theta is half alpha t square. So L upon theta is A upon alpha, right? L upon theta is same as A upon alpha. Now let us try to find out this ratio of A upon alpha. This will go, this will go, this will go, and you will get L upon theta as 4 times k square upon r, right? Okay. Now suppose during rotational motion the linear distance covered is S. The linear distance covered due to rotation is suppose S, then you know S is equal to r theta. So instead of theta you can write S upon r here, or you can say like this. Theta is S upon r. For k square upon r. Now transfer it over here and you will get L equal to S upon r into 4k square upon r. That leaves me with L equal to S into 4 into k square upon r square. So L is S into 4, and you know k square upon r square is 2 by 3. So L is 8 by 3 times S, or S is 3L times 8. So this linear distance is spent in rolling. So friction will not do work over this distance. 3L upon 8 is spent in pure rolling, and therefore as it is spent in pure rolling, friction will not perform any work. The friction will perform work only when it is skidding. Now out of a distance L, 3L upon 8 is spent in rolling. So remaining distance must be spent in skidding, obviously. So what is the distance spent in skidding? So D, it is total distance minus distance spent in rolling, and that is 5L upon 8. So what is the work due to friction? the work by the friction will be F into D. What is F? Mu mg cos theta into D. Now put the value. Mu is 1 by 5 tan theta into mg into cos theta into 5 by 8. 5 will cancel. Tan into cos is sine, so you will get mgl sine theta upon 8. This is the work done by the friction. It is mgl sine theta upon 8. I know this is a different aspect of a problem. If they ask you, you should be able to solve. Otherwise, of course, it is not asked in Hcverma. Now we can use a different approach. We can use work energy principle and we can find out the energy. So let us do that also as an interesting study. Now you can use work energy principle and you can find out the energy of the system after it covers the distance L. Okay, see here. I will represent a sphere by a small thing so that there will be no confusion here. Suppose this height is h, this is theta and this is L. Then obviously sine theta will be h upon L. So what is the work done by weight? You remember the work energy principle. Work done by weight is positive when it is coming down. It is plus mgh, that is mgl sine theta. What is the work done by friction? You know work done by friction is always negative because it is opposing the motion. Now we'll use change in the kinetic energy is equal to work done. So final kinetic energy is E, initial kinetic energy is 0, is work done by weight, and work done by friction gives you mgl sine theta minus mgl sine theta upon 8. You can see 1 minus 1 by 8 is 7 by 8 and you will get the same answer, 7 by 8 into mgl sine theta. To just remember this as another aspect of this problem, where you have to find out when there is skidding as well as rolling, how much distance is covered in pure rolling and how much distance is covered in skidding. The friction will do work only over the skidding part and not over the rolling part. I know the sum is complicated, but please take a good look at it. It will provide you a good aspect and a good solid fundamental understanding of the topic. Thank you so much.